Okay, welcome everybody. So today Cole's going to be talking about a symplectic setting for mixed stabilizer circuits. Take it away.
Thanks, Alex. Okay, so the structure of this talk. First, I'm going to give like a very brief overview of linear relations and symplectic linear algebra. And then also the stuff that we did previously on this topic with like Lagrangian relations and stabilizer circuits. And then like the new part of the talk will be on like adding discarding to this Lagrangian picture, and then talking about really nice properties that it has and what structure it has. Okay, so there's this observation made in Fabio Zanazzi's thesis that the phase-free fragment of the ZX calculus, that's to say the fragment is generated by the Z and X spiders, that this is isomorphic modulo scalars to this category of linear relations over FP. And the idea behind linear relations is that the morphisms are linear subspaces of a vector space, and you compose things with relational composition. So if you have a morphism from N to M, a subspace like this, and then one from M to L or something, then you would compose them if there's an element in the intersection of things. Okay, and yeah, so for this talk, pretty much we'll just care about linear relations over FP because of this interpretation in terms of the ZX calculus, but all of the pretty much all the things in this talk like generalized to any field, not just FP. And yeah, for an arbitrary field, this category is not just generated by two spiders. There's also an element for every element of the field that is like it's a map from one to one. And there's this useful observation by Pavel in his blog on graphical linear algebra that we'll be using. The color swapping functor in the ZX calculus corresponds to taking the orthogonal complement of linear relations. So you have the morphisms being linear subspaces, but in this setting, the color swap has this interpretation that when you do this, it's taking the linear or taking the orthogonal complement of a subspace. Okay. And we're actually going to be working with a bit more than linear relations. We're going to be working with affine relations, which were presented in this paper by Bonchi et al. And the idea is you add one more generator that is deleted here, copied, and when you compose it with the black spider on one of arity 1, then it like cuts all the wires into. And the interpretation of this in the ZX calculus is that this 1 is like adding ket 1. Okay, and yeah, this is now I need to go over some kind of technical background about symplectic vector spaces and symplectic linear algebra. So a symplectic form for some fixed n is this bilinear map omega from k to the 2n to k times k to the 2n. This should be down to k. And what it does is you think of k to 2n as like being composed of two subvectors. So think of the first one as like the position coordinates and the second one as the momentum coordinates. Then the symplectic form does this thing where it takes the inner product of the z and x over the position of one and the momentum of the other, and then takes the difference. So a finite dimensional vector space with a symplectic form is always isomorphic to one of this particular form, and you call a vector space equipped with a symplectic form a symplectic vector space. Okay, so just as there is this notion of orthogonal complement for just an arbitrary subspace, when you're looking at subspaces of symplectic vector spaces, you can take the complement with respect to this form instead of with respect to the standard inner product. So we denote when you do this operation to some subspace W of some symplectic vector space k2 to the n, we'll denote it with the the omega as a superscript. And okay, these are some really important properties of linear subspaces of symplectic vector spaces. So when the symplectic dual contains the subspace, it's called isotropic. When it's contained within the subspace, it's called coisotropic. And when it's equal, it's called Lagrangian. And these are really important, and we'll get back to them later. But this is some sort of like a restriction on the subspaces so that they obey the relationship between position and momentum in some way. Okay. So just as you have a category of relations and a category of affine relations, there's in fact a category of affine Lagrangian relations. And the morphisms now are these Lagrangian subspaces with an affine shift. And composition is the same as in linear relations, so relational composition. And in previous work, we showed that affine Lagrangian relations are generated by doubling all the linear relations with respect to the orthogonal complement. So this color switching functor, you think of it in ZX terms, and then you add 3 more generators. So the first one is the Fourier transform. The second one is like the phase shift gate. And then the third one is like the X gate. So here we're like, this is the Fourier transform in a way because we're swapping the position and momentum and negating one of them. Here we're adding from the position, multiplying by a scalar and adding that to the momentum, and then here we're just adding 1 to the position. And there's this really nice result, in my opinion, that we showed that for an odd prime p, this prop of affine Lagrangian relations over fp is isomorphic to stabilizer circuits, qudit stabilizer circuits, where the dimension is p. So in a way, by doubling phase-free ZX diagrams, and then you can get the full like stabilizer fragment. Okay. And please ask questions if there's something that is confusing or that I could clarify better. Okay. So one thing that is that you can define in this category of affine Lagrangian relations is something called Weil operator. So if you take a pair of elements of take an element of a symplectic vector space k to the power of n, then you can define a Weil operator just by induction, by pretty much adding x and z to the position and momentum. And for an affine Lagrangian relation f, if you compose f with this Weil operator, if it's a stabilizer of f, then this is equivalent to it being in the affine Lagrangian subspace, which f represents. So this is a very nice or very important thing to know. Okay. So we say that.
Cool.
Yeah.
Can you go back a slide?
Yeah.
This xz and f, I don't see how it is well typed, because xz is like a single element of a vector and f is a relation, right? So how can it be this single thing be in f?
So I think I've kind of made a typo here, but one way you can I would think of this as like the base case of the induction, and then so it's like this is for n is equal to 1. This is how you define it, and then when n, and then every time you just place them beside each other. So like you have an array of, say if you have like n different x's and n different z's, and you put all the x's beside each other in a string like this, and then all the z's beside each other in a string, so that like you're taking the ith component in the x grading and then adding xi to it, like z, like
So no, my question is more about, you have this composition below f with the while operator, and I can imagine how you generalize the while operator to a bit string of values instead of just a single value.
Yeah.
But f is a relation, so it should take the k to the 2n as input and then output k to the 2m. So like, how can you say xz is an f? Like, don't you need to have a pair of things that needs to be?
Oh, sorry. Yeah, I should also specify that f here is just as a relation as a state. So this is like a.
Oh.
Yeah, I didn't say, which is kind of confusing. So imagine that f is just a relation, say from 0 to 2 to n.
Yeah.
And then yeah, because for like a lot of this stuff, I'll just only work with states because it's just easier to do because it's compact closed.
Right.
Yeah. So like think of f as like a stabilizer state, and then if you have this stabilizer equation, then this is equivalent to saying that this is like in the subspace x and z.
Mm-hmm. Okay. Yeah, that makes sense. Thanks.
Okay. So just as you can do for pure stabilizer states, you can do in the general affine Lagrangian picture. So you can add mixing kind of just axiomatically by looking at the CPM construction. So recall that the CPM construction, what it does is it takes it doubles things and then adds you can add a trace as another generator between the doubled things. But now like the setting that we're going to be working in for the next 2 slides is in this category CPM of affine Lagrangian relations. So if k is odd prime, if k is fp for p and odd prime, then you can think of this as stabilizer circuits with the maximally mixed state. So you said that the stabilizer of a mixed circuit of this form, so f purified in this way, is a Weil operator such that this equation holds. So it's like if you plug it in on the one side, then it disappears. Not just on both sides, but only on the one. Yeah, and we use this notation for this bang. Just means the cap. So this is just the thing you're going to be tracing out. We have this result that yeah, the Weil operator is a stabilizer of the mixed state of this form, if and only if the part of the if and only if so okay, A is a stabilizer of the mixed state here, if and only if we can decompose sorry, I've made a typo. This should be f followed by 1 tensor A is equal to f. So the idea is that like we now get a stabilizer of f instead of just this mixed state, but on the wire that is being traced out, we can just put the identity in there. Okay.
Sorry, do you mean going back a slide? What's this notation where you have a mixed circuit f in brackets and then semicolon bang plus 1n? So I know that the bang is a discard map. What is the semicolon part of an equation?
I just mean it's just like so you're taking this pure state CPM of f, and then you're following it with 1 tensor to discard it. So like this is just the opposite of like the circle operation. Like you know, it's just the composition, but in the other order. So like.
Yeah, sure. So when you have in the top one in the definition of one, you have bang plus 1n, and in the bottom you have 1 times bang.
Oh yeah, sorry. This should all just be
what's
plus.
Going on here?
This should all just be
right.
plus.
Okay.
Yeah. So yeah, maybe I've had like some typos in this slide, so maybe it's not clear what it's trying to convey. But the idea here is that yeah. So if you have a stabilizer of some mixed state, then you get a stabilizer of a pure state by taking the part that's being traced out and then just making this 1. So here, like you'd have W of X and Z is a stabilizer of this mixed state, but then one tensor WXZ is a stabilizer of F, and this is biconditional. So this characterizes all the stabilizers of F. And what this allows us to show is the essential uniqueness of purification for all of these circuits in CPM of affine Lagrangian relations. So obviously, like for stabilizer circuits, this is already known, but this is just kind of a bit of a generalization to the arbitrary fields. So this fact about the stabilizer, the relationship between the stabilizers of mixed states and pure states allows us to prove this thing about essential uniqueness of purification. So if you have two affine Lagrangian relations with the same stabilizers, then you can just apply isometries to the pure states to make them equal. Yeah, so you have to like add some ancilla, and then you use this interpretation that that the isomorphisms in this category correspond to like to row operations, and then you can prove the essential uniqueness in general.
Oh.
Yeah.
So this notion of a stabilizer for a mixed state is kind of weird, right? Because it's only on one side. Is this coming from the literature? Like, is this like the standard definition of what it means to be a stabilizer of a mixed quantum state, sort of multiplying on one side by a Pauli string?
Yeah.
Or did you come up with it to prove this theorem?
No, this is like the standard notion, because if you think of like if you're drawing like think of how you would draw a stabilizer of a mixed state in terms of like you know, a bracket notation, then it's like you're like multiplying on the right by the stabilizer, and then it's kind of like asymmetrical thing. Like if
Right.
Like if you
Yeah,
have,
and I guess you couldn't say the stabilizers are the things where it's the U, where U dagger row U equals row, because you've kind of lost the phase if I put the U on both sides. So for instance, I can't tell the +1 eigenstates from the -1.
Yeah, I mean, obviously in this picture that we can't get phases anyways, but that's a different point.
Yeah.
Yeah, but this is the standard notion of stabilizer, which actually confused me for a bit, because I thought, oh, it should be something on both.
Something symmetric, yeah.
No.
I mean, that's normally the way you lift things to density operators, right? But I guess stabilizers are an exception.
Yeah, this is kind of strange.
Cole,
Yeah.
this stabilizer diagram doesn't live in CPM, does it? Because you're not preserving this doubling kind of thing. Because you could get something non-positive, like this is why like you have like a -1 kind of eigenstates.
Oh yeah, this doesn't live in CPM. This lives if you like go back and regard the CPM diagram as a diagram in this on the Lagrangian relations.
Yeah.
Yep. Okay, yeah, then you can do this, get the essential uniqueness of purification, which is kind of shows you what characterizes the stabilizers a bit. Okay, and now this is like the part that I think is kind of cool. So there's this, just as there's a prop of Lagrangian relations, there's also a prop of coisotropic relations. And the idea is you add as a generator this double discard thing. So this is like one wire that discards the position and the momentum. And of course, you can also add the affine stuff and get a category of affine coisotropic relations. And there's this result that we showed that the affine coisotropic relations are the same as CPM of the affine Lagrangian relations. So it's like, instead of doubling to discard, you can just straight up add the discard relation. Yeah, and the way that this is shown is so since both of these categories are compact closed, you just have to look at the states and show that there's a functorial, like well-defined bijection. And
Is sorry, is affine quotient rel just have ones as well as what's in quotient rel? Is it the same transition from as it is from lagrel to afflagrel?
yeah, you just add this this like X gate thing. So on the one wire
Right.
it's identity, on the other one you just do +1. Yeah, so
Okay.
like so yeah, just add you can just see this as adding this discard to the affine Lagrangian relations. Like there's this whole zoo of like different nouns and adverbs and stuff, adjectives, but yeah, and the way that this is shown, like the crucial part is using the essential uniqueness of purification. Yeah, so in particular, the affine coisotropic relations are up to scalars isomorphic to mixed stabilizer states in the sense of like being there's stabilizer states where you add discarding. This can be characterized by the affine coisotropic relations over FP. Okay, and then there's this kind of neat little thing that follows from this that so in the previous work we showed that the CPM of linear relations is Lagrangian relations, but here we show that if you take CPM of Lagrangian relations you get coisotropic relations. So you get this chain of, if you do CPM twice with two different conjugations, the first one being the orthogonal complement, the second one being like the kind of generalization of complex conjugation, then you get coisotropic relations. So I think that's just kind of cool. And also, this kind of gives you a nice account of the relationship between additive classical codes and stabilizer codes. So an additive classical code is just like a linear subspace of FP, and a stabilizer code is like actually exactly a affine Lagrangian subspace. Oops. So to get from an additive code, you do this doubling once, and then you just take this embedding where you can add the X gate, and then you take the CPM again. So there's this nice kind of chain between the classical error correction codes and the stabilizer ones. Yeah, and one thing that you can do in this setting, so as opposed to in the case of the traditional case where you just regard stabilizer circuits as matrices. Here, when you look at the decoherence maps for the Z and X observables, so here I have the X multiplication and the Z multiplication, and then instead of discarding, I have this double discard relation. So it's not the tracing, it's not the tracing in CPM, it's this double discard relation. Then we get to the decoherence maps are the things that like forget the stuff on the X and on the Z wire, depending on if it's the decoherence map for the X basis or the Z basis. So if you want to like work in a multi-sorted prop where you have a type of wire for a classical wire and a type of wire for quantum stuff, then what you can do is just like like people have done before, you can split the idempotent corresponding to the decoherence map. So in this case, we'll just split one of them because it's equivalent to splitting both of them. So what happens when you split the decoherence map is it's the same as looking at the category of this affine coisotropic relations, and then you add these two extra relations. So one that just inserts like the plus state on the one wire, and the other one that just post-selects for the plus state on the other wire. So this might be a bit like confusing. Oh yeah, and the colors are just so that you know when things type properly. It's still the same wire. There's nothing fancy going on. But yeah, just as an example, So there's, in the picturing quantum processes book, there's this, they give this nice picture of quantum teleportation. But in our case, every wire now is now split into two. And because the quantum teleportation algorithm only uses stabilizer circuits, then we can do it in this setting. So okay, here on the bottom, what we do is first we take the C naught, right? Or in this case, it's like the qudit C naught. Then we measure the Z and X observables of both of these wires. Here we have the maximally mixed state. We do the phase correction. And what I think is kind of interesting here is that in the normal graphical proof of correctness of the quantum teleportation algorithm, at some point you have to use the Hopf law between the Z and X observables. But here the Hopf law is not ever invoked. Really all we do is we just fuse all the spiders together. And then here, and we get that it's identity. So I think this is a kind of interesting view on the quantum teleportation algorithm, that in the symplectic setting, it says it's really just a matter of like topological connectivity. And that's all I prepared. And here's some references for the graphical affine algebra, this paper on Lagrangian relations, graphical linear algebra, and then this thesis of Sanazi on interacting Hopf algebras.
Yeah, thanks, Cole. I'll give a wee clap now, I guess, and ask some questions. So I'm not sure if this is already entailed in what you described, but does this mean that this comes with a calculus which is, for example, complete for stabilizer circuits?
So the kind of the catch kind of is that since everything is doubled, then you kind of can appeal to the completeness of, say, the graphical calculus for linear relations, or or completeness for the phase-free fragment of the ZX calculus, but like only on this kind of doubled level. You don't immediately get completeness in the sense of like, right? Like if you look at how we defined, like this generator, right? These are individual generators, but they're actually composed of smaller generators. So we only have completeness of the small ones, not like the bigger picture. Yeah.
But Cole, I'm sure you're familiar with the paper that I think Titwan is an author on as well, with where if you have a complete calculus, then you can freely add a discard, and then add the relations that tell you that certain things must be isometries with respect to this discard, and then you have a complete calculus there. And I guess like freely adding a discard is kind of like CPM.
Yeah, I mean, yeah, I think there's some really close relation to what is going on in their paper and what's going on here, because they show if you have like that in a lot of these really nice settings, and in particular the qubit stabilizer setting, that just freely adding discards or freely discarding isometries is the same as taking the CPM kind of trace. And here it's actually like a discard map. So this surely does discard all the isometries. It discards all of like the injective maps. So I don't know what the deep connection is there, but in their proof for the stabilizer fragment, they use the essential uniqueness of purification. So there's kind of yeah, like their techniques are the same. They're saying something very similar, but I don't know exactly like what the exact relation is.
So I was also wondering, because you have this, if you do CPM twice, this result that you have the co-isotropic things, yeah, that go back. No, the other one, other slide.
Oh, the other side.
Just was this one, yeah. So affine co-isotropic things, those are, you have still 2 wires, but in the CPM of affine Lagrangian, you have 4 wires representing a single system.
Yeah.
Is that correct?
Yeah.
So this double discard somehow allows you to talk about these 2 wires in the co-isotropic thing as if they're 4 wires, or the other way around?
I mean, I guess it's not really like a directed thing, but like normally when you take CPM, it doubles the amount of wires. But here, this isomorphism allows you to just keep the same number of wires and just add more maps. So I guess
I guess I'm just wondering, because both of these things, both sides of this equivalence are a prop. So surely this equivalence must be mapping each generator to a generator on the other side.
Oh yeah, so it's mapping on objects. It's taking, so the prop here is like the generating wire here is the vector space, say k2 to the n, or no, k to the power of 2, and then here it's like k to the power of 2 times 2, so k to the power of 4. So these are both props, but like this one, there's on the left hand side, there's always 2 wires bundled together, and then here there's like 4 wires bundled together. Right, and then in like stabilizer circuits, there's 1 wire.
Yeah, and then I guess this double discard in the co-isotropic thing is mapped to 2 cups or something in the CPM of the on the right hand side.
It's mapped to like here, for example, like this is the co
right
cap, I guess. So yeah, it's like this thing where you have the one in Z basis and the one in X basis. Yeah. And the CPM is with respect to this functor that is like you know, like it's like the generalization of the dagger functor. So it's a specific CPM that you need to use, or a specific conjugation for the CPM.
Yeah.
Basic question. The product is the direct sum of these vector spaces, right?
Yeah. Yeah. So like this is why I haven't had that typo, because on the here Athline, in the Athline coisotropic stuff, and in the CPM of the Athline Lagrangian stuff, it's the direct sum, because these are in the applied to stabilizer circuits, these are subspaces of fp to the power of n or something, or fp to the power of 2n. But then on the stabilizer side of things, this is the tensor product of vector spaces
Right.
over the complex numbers. So I mean, you can, I mean, I'm thinking of it as like it's the bilinear tensor product, but that's because it's on the other side of this isomorphism it is, but on this side it isn't. Yeah.
Right. So your functor is taking a direct sum to a tensor product.
Yep.
I wonder then whether this could be useful for, again, naively, like circuit optimization or something for stabilizer circuits. Again, if they're small enough that the blow up you get from the direct sum isn't too big.
Yeah, I mean, this is like the difference in the tensor product. On the left-hand side of it's the direct sum, and on the right-hand side of it's the bilinear tensor product. I think like this is one way you can think of the Goldman-Nil theorem, like, or not directly, but like I think this is like a very similar thing going on, because like on the left-hand side there's just, you can only count. It only, like, the things just grow way less fast, right? And there's just less there's just less things going on because it's the direct sum. But on the other side, you're doing multiplication instead of addition, so things grow exponentially. So that's how I think of this as this difference in tensor product as kind of like a consequence or like a different perspective on the Goldman-Nil theorem.
Yeah, so that middle category can really be seen as a category of stabilizer tableaus, at least for odd prime dimensional fields, and then that's isomorphic basically by Gottesman nil to the associated stabilizer category.
Yeah.
Right. Okay. Yeah.
Yeah, and I don't know if this would be useful in circuit optimization, but like this diagram you actually like can be interpreted as both a diagram for stabilizer circuits or as a diagram in the phase-free ZX calculus. So you can always like simulate stabilizer circuit just using phase-free stuff and doubling it, and then for discarding you just add the two white spiders.
Well, is that true? Because you also need the Fourier transform thing, right? The negation thing.
Yeah, but here. So the Fourier transform looks like so this is the antipode, which you can draw using the Z and X spiders. Right? Like you take like a Z cup and a X cap.
Oh right, yeah.
And then this is the X thing. So this would be like, I mean, in the yeah. So you need the X. You need to do the affine stuff. You need phase-free plus the X gate. So it's like you have two copies of the ZX calculus, or two wires that in the phase-free plus X gate fragment, and then the X gate now like it now lifts to identity wire on the left, and then X gate on the right.
When you say antipode, is this the antipode of a particular Hopf algebra or something?
It's
or
the
is this
antipode
more
between
in a more general sense?
It's the antipode between this black and the white one.
Okay, right.
So if you interpret this as copying and this as addition, mod p, then this is -1 or p + 1. Yeah.
And so you get some kind of Hopf law out of this thing.
So I mean, you assume that you have the Hopf law already in the phase-free fragment.
Right. Okay. Sure.
But then when you double it, then you also get the Hopf law, because you double when you take the CPM thing, you take the say the white. If you take the white multiplication, then here you get the black one and the white one, and then conversely you get the black one and white one, and then on both sides you just apply Hopf. So it like all, yeah, it's faithful.
Cool.
Cole, you had this slide where you were showing additive classical codes going over to stabilizer codes.
Yes.
So I'm just wondering, because I think there's a way of thinking of stabilizer codes as additive codes over a quadratic field extension, over a quadratic finite number field. So I'm just wondering if that's somehow related to this picture at all, if secretly you're taking a quadratic field extension somewhere. Have you thought about this at all?
I haven't thought about that. Do you have a paper that mind, or I can
It's I guess back in the early days of quantum codes, people were talking about codes over the field GF4, over the Galois field GF4.
Mhm.
So that's the kind of stuff I'm talking about here.
Yeah, so I guess this doesn't work in the qubit case. So P has to be
Okay. Yeah. I mean, I think the quadratic number field stuff is more general than the qubit case.
Oh,
so there's GF9, and I think there's a paper talking about stabilizer codes or codes over GF9, additive codes over GF9 as qutrit stabilizer codes.
I should look into this, but I would assume it's the same kind of thing.
I think that the thing that's closer to this actually is CSS codes. So where you have a quantum code which you can regard as a classical code that's self-dual in a certain sense. And the sense in which it's self-dual is with respect to this Lagrangian inner product. So I think it's you have the classical code kind of right at the bottom there, and then you lift it to a kind of doubled version of itself, which is going to be self-dual in this sense.
Yeah, and then
Okay.
I don't know, like additive classical codes, or like just additive subspaces, not affine subspaces. At least the ones I've come across. So you also have to like add the affine stuff as well.
Yep.
But, yeah, so if you have something that's not affine, and then you double it, then if it's self-dual with respect to this symplectic dual, then it's an additive code. Yeah, but I definitely want to like look a bit more into this, because this is just kind of, I just put it as remark because I need to like look more into it.
Okay.
So Cole, have you had any new ideas about how this might work with qubits, or do you think it's just too much of a mess for F2 to actually try this stuff?
What?
Because this is all odd prime stuff, right? So in places where the toy theory and stabilizers are the same category.
Yeah, so for this, I'm not so sure, but like what you could do naively, which is probably not sound, is you could just add the Frobenius equations between the black spiders and the white spiders, add like the Hopf law, and then just add all of these things manually, but it just doesn't have this nice semantics, because linear, there's no when you take matrices over when you take linear subspaces over something that's not a field, then you can't do this relational composition. So I don't know. I've like kind of thought about it, but I haven't had any new clues. But I feel like it should be possible in some way, but I'm just not taking the right approach.
No, F2 is a field, right? But you have this problem with the signs in the stabilizer tableau, right? You have to keep track of the signs, which is only a problem when your dimension is even.
Yes, I would think you would want to do it over like Z mod 4Z or something.
Oh yeah, that's right. That's how we were talking about it. And then everything is just a ring, right? Which makes it a bit of a mess.
Yeah, and then you'd have to take some sort of quotient, which I don't know what it would be. And also if you look at a Frobenius algebra and you look at the phases for the Frobenius algebra, so like for the X Frobenius algebra in this doubled picture, then it forms a torus. So if you just kind of by hand did this all with over Z mod 4Z, then the phase group would be Z mod 4Z squared, which is like not the block sphere. This is the torus. So you'd have to like somehow turn this torus into a sphere by some quotient, which I don't know how that would work.
Yeah, like kind of breaking my head. Think about that.
So I guess sort of related to this, like if you have ZP, then it is stabilizers over p-dimensional qudits. What if you have like just like a different group, like I don't know, like say a p-squared kind of field? Can you then define a different type of stabilizers? Like it would still embed in qudits somehow, but now your stabilizers are different. Like you get the different efficiently simulable quantum subset of stuff.
So what field? You just over any field, or?
No, so as far as I understand, all the finite fields are form p to the n, or like let's say p to the k, so I'm confusing, for some prime number p, right? And we know that like fp corresponds to regular stabilizer theory.
Yeah.
So if you have fp to the k for some k, like k not equal to 1. Can you then define a different type of qudit with like different z and x operators that still gives you a stabilizer-like thing?
Yeah, so I mean, all of this stuff with about stabilizers and purification and stuff holds for any field.
Mm-hmm.
But I don't know if you choose some field that is not FP,
Mm-hmm.
then I don't know like what the interpretation would be as.
Yeah. So I guess that's my question. Like, for any finite field, can you find a interpretation into linear maps with tensor products? And of course, for F2, there's like a problem there. But
Yeah, I'm not so sure if you can or not. I'm not sure. But as a kind of a side note, as I said in the past, if you look at the field of real numbers or the real rational numbers, I think it's called, like where you add, you take the polynomials over the reals and you add the inverse to the polynomial, like the element you're adding. Then you can interpret these in terms of like electrical circuits, but that's obviously not the finite field. So there are other fields you can play with, but I don't know other finite fields. I'm not so sure what if you can interpret this as like in F field or something.
Okay, it seems like we've hit a bit of a lull, unless you have
can I ask you one more question? So cool. I know you were like on a quest to sort of rederive ZX from like taking a basic prop and then like doing pullbacks of props and distributive laws of props and all that.
Mm-hmm.
So with these results, like what's the status of that project now? Like what is like what can't you do in this way?
Well, I suppose this is yeah. So when you look at like the phase-free fragment of the ZX calculus, you can do it with that, and you can also do it with the phase-free fragment with the X gate. But here, there's not like a distributive law. It's or like a limit or something. You're taking CPM, so here you're kind of forced to like. I mean, CPM is not this like nice categorical thing, really. So you're forced to do this this kind of weird doubling. Yeah, I don't see how this could arise in terms of a particularly nice distributive law between like two copies of the phase-free ZX. And yeah, so I think you're forced to do the CPM thing. And past the stabilizer fragment, I don't know if there's much hope, because things might just become too complicated.
So you say CPM is not a nice categorical thing because you have to make this choice of conjugation, right? Is that the reason?
I mean, I would say, well, it's not a nice categorical thing because there's this like, well-known result that CPM is not a monad, for example, and also it's not a limit or a co-limit or distributive law, which is like, these are things I consider to be nice just from a personal like aesthetic point of view. But I still think there's this kind of nice symmetry going on because it's like, you still have left and right sided things that are related somehow. But yeah, I don't know. I think you have to use these. You can't use the traditional kind of categorical methods to kind of compositionally do it all.
So just to recap, the status of the kind of spans and distributive laws of props to build ZX is you can get ZX with phase-free and pi phases, but you can't get stabilizers. Is that true?
Yeah, so it's well, I mean, the stabilizers are, this is still a category of relations, but just the way that you're composing the constituent parts changes when you go to stabilizers, because you can't compose things by like some limit or co-limit anymore. You have to like define it, or like the only way I can see that you can take the smaller things and compose it into a bigger thing is by taking CPM. So it's just kind of a different flavor than the other things.
Right. So up to this point, you can get there with kind of universal properties, but afterwards you have to make it up as you go in that sense.
Yeah, but still, this is still a category of relations. So you're still, composing things with limits and stuff. But it's just when you take the smaller constituent parts, then you're not like you can't use these like limits and colimits in a nice way anymore. But but I think CPM is still kind of nice in a different way.
Okay. Let's all give another round of applause for the speaker. Thank you very much.